ladies and gentlemen. My name is Delichristov, and I'm representing here virtual vehicle company from Graz and OBELICS cluster 1 and 2 with next generation electric vehicle design. The first use case from our cluster 1 is the Renault Trucks Volvo Group with his analysis of the alternative electronic powertrain architectures for the next commercial electric vehicle development. As you can see, this company offers a bright portfolio of vehicle applications and powertrain architectures. For our OBELICS case study, we choose the layout 2 with one axle with 2 electron machines and multiply transmission system. So the main aim of this use case was to choose the optimal powertrain architecture for the future, respect to the optimal efficiency, vehicle efficiency, and the development costs. To achieve this result was developed workflow methodology and various tool chains like powertrain architecture optimization toolchain, component design optimization toolchain, component sizing or powertrain control optimization toolchain. And all these toolchains were merged or integrated to one engineering tool, which then enabled faster analysis and optimization of electric powertrain concept in early project phase. As a result, you can see, for example, this electron machine sizing optimization, optimization generation, or this example, yes, with 1,836 alternatives designs were generated, or transmission design variants generation with 29,376 powertrain configurations evaluated in 7 hours. And the results you can see below down on the right side for different driving cycles and different variants, design variants, efficiency improvement potential. The second use case from the cluster 1 is Ford AUTOSAN e-truck. This study of 18-ton rear-wheel driven electric truck has one target, and this is the optimization of configuration based on analytical development with different inputs like vehicle specification, different driving cycles, or components optimized sizing. And OBELICS target is, of course, the time development reduction and optimal efficiency improvement. To achieve these results, a lot of tools, for example, especially 7 tools were developed within the OBELICS. And one of these tools, for example, the interface model generation tool, can automatically generate it, fully automatically generate it, plant and control model, and based with input of the predefined interfaces. So the match of these interfaces, plan model, and control system model, we can see, for example, with this interface model generation tools, improvement on the time development at about 67%. And the next example is the control strategy, which was implemented to the gas pedal. And with this control improvement strategy, we achieved 7.5% improvement on this Ford AUTOSAN e-truck. So right now, I'm taking over my speech to Nicola Tobia from FIAT company with his next use case, FIAT 500E. You are welcome, Nicola.
Thanks, David. I try to share my screen.
You can.
Can you see me?
Yes, we've got it.
Okay. Hello, everybody. This is Nicola Tobia from CRF, that is the research center of Fiat Chrysler Automobiles. In OBELICS project, we had some use cases based on the reference vehicle Fiat 500e, shown in the slide. That is a battery electric vehicle sold in the US since 2013. The objective of this use case was to create a virtual simulation capable of integrating the entire vehicle with all systems and subsystems in order to improve efficiency and autonomy of this vehicle. So first of all, we proceeded with the creation of the model and its parameterization. We used for this SimCenter AMESIM for modeling the entire vehicle in 1D to replicate in whatever driving cycle all systems that have a role in the energy management. Then a methodology was implemented to couple this 1D model to 3D CFD computational fluid dynamics models, in particular two, one for the external vehicle and one for the internal vehicle, using star CCM. This in order to obtain a higher fidelity simulation, in particular for thermal management. To validate the model, we perform some tests in FCA climatic wind tunnel for different scenarios that are shown in the table. So two standard cycles, NDC and WLTC, and with different external temperatures, -10, 23, and 35 degrees. As we can see from the animation on the bottom right, that shows the comparison between experimental and virtual results, our model gave us a very good correlation. Once validated the model, we proceeded with the optimization of the vehicle in order to improve the efficiency. Here are listed on the left some of the improvements that we analyzed. The insertion of a double gear ratio transmission, the regenerative braking improvement, the controls optimization, the e-motor inverter newer technology, the heat pump for air conditioning system, and an eco-mode for cabin ventilation. In order to test this efficiency improvement, we calculated a matrix of different scenarios composed by the combination of different external temperatures from -10 degrees to 35 degrees and different real driving cycles, urban, extra-urban, and highway. Finally, we perform a weighted average to obtain one single number for efficiency improvement, and it gave the huge improvement of 20.5%. To conclude, we can say that thanks to this work, we obtained the following results: an environment for virtual integration, multi-physical and scalable models, a methodology for development effort reduction, because thanks to this virtual optimization, we can avoid several physical tests, and also for efficiency optimization with very good results, thanks to this good analysis of systems interactions. And finally, also a methodology to couple 1D and 3D that increases fidelity and can be interesting for the study of several phenomena. Finally, I would like to thank all the contributors for their great cooperation in this work of Fiat 500e, in particular CRF and FCA, Siemens, Virtual Vehicle, University of Ljubljana, FH Janum, SIA, and University of Florence. Okay, that's all from me, and I leave Mathieu his use case.
Okay, thank you. Mathieu?
Yes, my name is Mathieu Sarrazin. I'm a research manager at Siemens Belgium with a focus on mechatronic system testing and simulation. Our use case goes about model-based E-POWERTRAIN testing. The main goal for us is to reduce development efforts, and we followed for this the following workflow. So first we collected data, then we created different models and identified them with real measurements. Then we integrate these models in a brand new XIL setup and validate them with measurements on the roads. And finally, we could do explorative testing on the XIL setup. This video gives you an overview how it went. So we collected first reference data with our Simrod electrical vehicle. Different components were checked, and we did different measurements from electrical to system variables with a Siemens SCADA system. Everything is measured synchronously. Different types of roads were measured, like you could see here with our vehicle. Different types of heights were selected during these tests, also different types of speeds. We created our own Leuven driving cycle. The system under test is the inverter and E-motor. We replaced the vehicle components by test bench components and a real-time platform and the rest vehicle. Here you get a view on what is created during the OBELICS project. So that's our auxiliary, together with the real-time scalable model, which was running on the real-time platform, validated on the road, and allows us to replay on our auxil setup. We get a good correlation between the operational measurements and the repeatable auxil tests. The error is very small. And that allows us to perform some what-if scenarios. So you can change the body to have an influence on the aerodynamics, change the gear ratio, change the battery, subtract weights. And that's possible in the simulation model, which is running in parallel with real components without making a lot of new prototypes, real prototypes. Together with the University of Brussels and the University of Firenze, we achieved the project's objectives ranging from in-vehicle component characterization to accelerated explorative testing. By our development workflow, we could achieve a reduction in development efforts by 60 to 85%. And we see also an efficiency by 4.3% by doing the what-if scenarios that I discussed. And this brings me to the end of my presentation.
Okay, thank you, gentlemen. We have a question here, and it's valid for all of you. So maybe, David, you're still on the line, you can answer it. In the first use case David showed, the tool helps to find a better optimum and find it quicker. How applicable do you think the tool is on other vehicles, and can we expect similar advantages on other vehicles? David.
Andrew, I have to apologize. Sorry for this. I have to apologize, but I didn't hear you really. Could you repeat the question, and to whom was the question?
It was to Mathieu, but now you're here, you can answer it. Well done. So in the first case, you showed the tool that helps to find a better solution, a better optimum, and how to find it quicker. That was one of your use cases. How applicable is this to other vehicles? Would you expect similar advantages with other vehicles?
Well, if I can talk for our use case, you can use our workflow approach for every type of drivetrain you want to test in combination with the rest vehicle. It's just here a concrete example that we selected to show our full workflow from data collection to model creation and identification, and to auxil testing, and finally do some what-if scenarios. And in the models, you can easily change parameters to fit on the parameters of a new prototype or a different type of vehicle.
Okay, so it's easily done. A second question then, do you need another driver for that cool car? In which case, I'll give you my email. Okay, thank you, David, Nicola, Mathieu, thank you very much.